Now we have reached full inscrutability. It's very compact. G mu x nu. I'm even leaving out some of the complications because I like you. But this is, you see what's going on. We've taken the question, how do we generalize an arbitrary geometry? Well, you need to know the length of every curve. How do you encode that information? Here's how you encode that information in the values of the components G mu nu. Let's see that at work, okay? So G mu nu is the metric tensor. We've already secretly seen it. When Minkowski told us about space-time, he said that the time interval you measure, tau, is related to the coordinates t, x, y, z by tau equals t squared minus x squared minus y squared minus z squared. In terms of that little formula we had on the previous slide, that means that G mu nu is usually 0, right? There's no term in the equation that is x times y, for example. That's why you get all the zeros on the right here. But in principle, the rest of them you can read off. The G00 or GTT is +1, GXX or G11 is -1, and so on. And furthermore, all of these symbols have meaning. I mean, you knew that they did, but we can even tell you what the meaning is. The spatial ones, the x's, y's, and z's, all by themselves, not involving t, those really are just the generalization of Pythagoras' theorem, maybe in a curved spatial geometry. Those are the spatial distances. GTT, what is that doing? It's telling you how fast time flows. Now, that's an entirely preposterous idea, how fast time flows, because time flows at 1 second per second. There's no other rate at which time will never flow at 2 seconds per second, okay? But the time that you experience tau can flow at different rates with respect to the time coordinate. The time coordinate is nothing physical, it's just something that we use as a convenience. So GTT, that component of the metric, tells you how fast time flows compared to the coordinate that everyone has agreed to use. And then the ones that mix space and time literally tell you how time and space can twist into each other. Now, we don't have any of that in the Minkowski metric. That's not going on. You might say, like, when is time and space going to twist into each other? When will I ever see a major Hollywood blockbuster in which that happens? Well, you have. Because time and space twist into each other when you are close to a rotating black hole. This is a famous image from Interstellar, right? The movie. This is the black hole, Gargantua. And all of the image here, all of the little filaments of light, were calculated numerically by using a metric tensor which had significant rotation, twisting of time and space into each other. It was so much work that Kip Thorne, Caltech Nobel Prize winner, who is also the executive producer and inspiration behind Interstellar, collaborated with the special effects folks here in the UK to write a paper. I mean, they also made a movie, but they wrote a paper, more importantly, in classical and quantum gravity, where they explained all the mathematical details that go into making this picture. And if it weren't for the components of the metric tensor that let time and space bend into each other, it couldn't have happened. I hope you enjoyed that little pop cultural interlude, because that's it. No more of that. Getting serious once again. Okay. So Einstein is taught that Riemann figured out how to capture the information you need to characterize a perfectly arbitrary curved geometry. Now you need to put it to work. How do you make money out of this metric tensor? Because what you care about is not the distance along a curve. What you care about is the curvature of space-time. What does that mean? Well, if Euclid says that you start with two initially parallel lines and they stay perfectly parallel, and Euclidean geometry is flat geometry, then curved geometry is not flat geometry. Curvature is all of the different ways in which those initially parallel lines can fail to be perfectly parallel forever. So we have a way of characterizing this called the Riemann tensor, much better than the metric tensor, because the metric tensor only has 2 Greek indices. A Riemann tensor has 4 Greek indices. That's twice as many. And the game that you play is, you tell me what point you start with, what line segment you start with, what direction your initially parallel lines go at. You ask the Riemann tensor the question, what happens to them as I extend those lines? And the Riemann tensor tells you how they twist around or converge or diverge or whatever. So the Riemann tensor is really capturing what you care about in the geometry, that is to say, its curvature. The g mu nu is the raw data, the metric tensor, but what you want is the Riemann tensor. So just to get this, in context here, we've seen secretly different kinds of tensors, different kinds of quantities that are geometric and have different numbers of components. A momentum in space-time. In ordinary Newtonian mechanics, momentum is a three-dimensional vector, but guess what? In space-time, it's four-dimensional because you have a time-like component as well. You've seen the metric tensor, 4 by 4, so 16 components. The Riemann tensor has 4 indices, so it is a 4 by 4 matrix of 4 by 4 matrices. And I swear if anyone says they see a typo in this, I'm going to smack them. Again, this is one of those slides you're not supposed to get any knowledge out of it. You're just supposed to be impressed and go, wow, there's a lot of Riemann tensor out there, okay? And if you're a graduate student in physics, in my day, you would calculate the Riemann tensor. These days, they have their fancy computers and everything, and they don't know what that's like. So this was a lot, so let me just capture what you're supposed to take away from this, okay? The geometry of space-time is what you need to talk about in general relativity. This is Einstein's insight. If gravity is a universal phenomenon, then it is not like electromagnetism or other forces. It is a feature of space-time itself. What feature is it? It's the geometry of space-time. He needed the math to describe that. He was taught it. It's Riemannian geometry or differential geometry. That can be arbitrarily complicated, but Riemann let us whittle it down to a little usable piece of information. How to calculate the length of every infinitesimal curve, and from that you can build up the geometry as a whole. That information, in turn, is captured in the metric tensor, 4 by 4 tensor in 4 space-time dimensions, and that tensor has a curvature characterized by the Riemann tensor. So in other words, the metric tensor and the Riemann tensor aren't completely separate. The whole point of the metric tensor is it tells you everything you need to know as long as you can extract it. So the Riemann tensor is defined in terms of the metric tensor. If you're a working general relativist, your day job is usually figuring out either the Riemann tensor from the metric tensor or some vice versa kind of version of that. The next question, if you're Einstein, is how are you going to use that technology to come up with a physical theory, a theory of gravity? Well, you knew what Newton did. Remember, this was not just showing off when we talked about this before. This is Newton's way of telling you the acceleration due to gravity, right? The acceleration depends on Newton's constant times the mass of the Earth or whatever it is causing the gravity, divided by the distance between you and the Earth squared, the center of the Earth in this case. So Einstein needs to replace both sides of this equation. On the left side, the acceleration due to gravity, he needs to have some measure of the curvature of space-time. On the right-hand side, the source of gravity. For Newton, the source is the mass of the gravitating object. What's it going to be for Einstein in this relativistic context? You already know it's not just going to be the mass, because Einstein told you that E equals mc squared, which is a hint that energy and mass are somehow unified. They're somehow part of the same thing. So mass is not the primarily important thing that it was for Newton. In relativity, mass and energy and heat and momentum and strain and pressure, all of these things are somehow going to be sources for gravity. What we need, I should ask if anyone can guess. Do you know what we need? We need a tensor. And we have one. I didn't give you time to guess. Sorry about that. I didn't want to be shown up by someone actually guessing. So the energy momentum tensor is basically another 4 by 4 matrix that tells you all of those things. It's called T mu nu, and it encapsulates all of the different forms that energy and momentum and other related quantities can take. And once again, we can look at it component by component. There's a 0, 0 component, or TT component, if you like. That tells you the energy, including the mass. That's what we usually think of as the amount of energy in the good old Newtonian sense. These diagonal components, TXX, YY, ZZ, that's the pressure. So we're thinking here not just of a single object like Newton would have thought of, we're thinking of maybe a fluid or a solid. So you take some little region of it and there's pressure in the X direction, the Y direction, the Z direction. Those different directions are the diagonal components of the energy momentum tensor. And then there are off-diagonal components which you can sometimes ignore, not always, but they tell you about how energy is changing and moving from place to place, the heat flow, the momentum, and so forth, okay? So all together, all the different ways that you can think about energy are bundled up in this tensor. This is definitely going to be something we're going to use as we construct the new equation for gravity that Einstein is looking for. We have the metric. The metric defines the Riemann tensor, which characterizes the curvature of space-time. Mass is a kind of energy, so we're beginning to see left-hand side and right-hand side come together. We want to replace Newton's equation, okay? There's an obvious guess that it's not going to last very long. On the left-hand side, acceleration maybe should be replaced by the curvature of space-time, which is, as we know, characterized by the Riemann tensor, r lambda rho mu nu. And the right-hand side of the equation, which has the mass in it in Newton's equation, should have the energy momentum tensor, T mu nu. So we have curvature of space-time on the left, stuff, energy, momentum, and mass, and so forth, on the right. It obviously doesn't work. I can just imagine Einstein going like, it was so close, and it didn't work. It doesn't work because the Riemann tensor is a 4x4 matrix of 4x4 matrices. The energy momentum tensor is a 4x4 matrix of numbers. They don't match up. They can't be proportional to each other. Fortunately, there were some very industrious Italians who read Riemann's paper back in the 19th century and figured out all sorts of things you can do to the Riemann tensor. Basically, you can distill it down. So you can contract, as they say, the Riemann tensor to make something called the Ricci tensor, after Professor Ricci. And the Ricci tensor only has 2 indices. And then you can actually contract that again to get something called the curvature scalar. So when Einstein is trying to think of what can he put on the left-hand side of his new equation for gravity, he has various ingredients to play with. He has the Riemann tensor, but also the Ricci tensor, and also the curvature scalar. Now you're instantly going to guess. I want to take the Ricci tensor, because it has 2 indices. I'm going to set it equal to the energy momentum tensor, which also has 2 indices. If you're guessing that, congratulations, you are just as smart as Albert Einstein, because he guessed that. It didn't work. It doesn't work because energy is not conserved in various other problematic things. But again, because he was Einstein, he worked harder, and he came up with this thing. R mu nu minus 1/2 r g mu nu equals 8 pi g t mu nu. That is the correct generalization of Newton's equation to the relativistic context, and we now call this Einstein's equation. You saw it a few minutes ago, but now you perfectly understand it. But the point is, you see why even if your understanding is only 99%, not 100%, you see that it's not just showing off or egregious, right? Like these symbols have meaning. These mu's and nu's talk about directions in space-time. They will take on different values, 0, 1, 2, 3. R on the left and G on the left are different geometric quantities telling you about the curvature of space-time. T mu nu on the right is telling you about energy momentum. G is Newton's constant of gravity. 8 and pi you've met before.